there was a problem in your homework assignment that said, well, that developed the idea of the number e, and we're going to develop that idea just a little bit. So we regard e as the limit of what you get, the limit of the growth, the factor that you get when you compound continuously for one period at an interest rate of 100%. Now if you do that, if your interest rate is 100%, then your growth rate is 1, which could be expressed 1 over 1. Your growth factor is going to be 1 plus that, which is of course going to be 2, raised to the 1 power. And of course that gives you 2. That means that if you just compound once a year at 100%, you double your money at the end of the year. Now if you compound twice, then you get to take half of your interest at the 6-month period and then apply the other half of your interest to that principal at the end of the next 6 months. What that means is in each period, each 6-month period, your growth rate is 1/2 instead of 1, but you get to do it twice, which is going to square it. Now 1 plus 1/2 squared is 2.25. Now we can go to any number of compoundings in a year. If we take 1/10 of the interest rate, but do that 10 times during the year, then our growth rate for each period will be 1/10, but we'll have 10 periods. And we'll have 1 plus 1/10 to the 10th. That gives us a factor at the end of the year of 2.59. If we go to 100 periods, we get about 2.71, maybe. Maybe we get 1 here. And you can calculate this, 1 plus 1/100th to the 100th, and see if that is indeed 2.71. Notice I just kind of halfway wrote that 1 because I'm not real sure about it there. Didn't want to take time to calculate it in class. But that's all right. I don't mind leaving that for you to validate. If it isn't 2.71, it's pretty close to at least 2.7. Now if we continue this to infinity, meaning that this number here, which is going to be equal to this number, becomes larger and larger without any limit, we get more and more decimal places, and e is going to be something that's approximately equal to 2.718281828. It looks like this repeats, but it doesn't. After the 1828 here, it just looks like random numbers. At some point out here, since this thing goes on to infinity, it's almost certain that 1828 will appear again. It's actually highly probable that it appears 10 times in a row at some point in this expansion, maybe out in the 20 billionth decimal place or something. But anyhow, this is the number e. Now the basic thing is e is between 2 and 3, maybe a little bit closer to 3. And if we compound interest continuously, that's continuous compounding at rate r, we can use a process much like the one we just saw to reason out that our principal function p of t will be p0 times e to the rt. Now this is just an exponential function. Remember that e to the rt is just e to the r raised to the t. So this could be written as p0 times e to the r raised to the t. And now we can see e to the r as being our annual growth factor, or the growth factor that corresponds to 1 unit of t, whatever we measure t in. Okay? So that's continuous compounding. Now, here's an important statement. Log to the base b of t is the inverse function to b of t. Well, log to the base e of t is the inverse function to e to the t. Okay? E is one of the two most important numbers in mathematics, arguably, e and pi, which have kind of a neat relationship. When you calculate the area under the normal curve, which is e to the x squared, from negative infinity to infinity, you get square root of 2 pi. So e and pi are somehow related, at least in that context. And the relation goes very deep, actually. In any case, log to the base e of t is inverse to e to the t. E is so important, and it's the most natural number in the universe, maybe, that we call log to the base e of t natural log of t. And that's what the ln key on your calculator is. It's the base e log.